well, I will show you a few examples of the uncertainties you get in the dust models, only a few, because there are, of course, many of them. So I will just show you 3 examples if we have time. So just to start, because not all of you might be aware of all this, well, what are the basics of all dust models? So first, you have to choose a chemical composition. So you go, for instance, and you ask Karine, what should I take for the optical constants of my silicates? And then you find someone else to find your carbons, etc. And then you have to choose how you mix them. Or you do it empirically. You also maybe want to add some inclusions, add some ice mantles. You have to choose your chemical compositions. That's a big source of uncertainty, just the choice. And then you have to give a structure to your grains. So they can be compact, they can be porous, they can have mantles, they can be single grains, they can be aggregates, they can be spheroids. So they can be any shapes. And this is, again, a choice you have to make. And of course, you have many ways of describing a single shape. So for instance, I have many ways of describing a sphere. So that's another source of uncertainty. And then you have a non-trivial step, which is also a source of uncertainty, to derive from all this what will allow you to calculate spectral energy distribution to compare with your observations or extinction curve. So you have to calculate absorption efficiencies. And if you believe the lab, maybe this will depend on temperature, another source of uncertainty. You have to calculate your scattering efficiency, your scattering phase function, and the heat capacity of your grain. And of course, there is another source of uncertainty that I will not discuss at all here, which is the choice of the size distribution for all these grains that you have calculated. So you have to choose minimum and maximum size. And then you have to give a shape to the size distribution. So log normal, power law, Amaren, or Werder thing. People choose whatever they want according to their objectives. So the non-trivial step is which model do I choose to calculate my optical properties? So here I put a few. Of course, it could be twice longer. This is just a table I give to students when they come for a training period with us. So, and here I have a list. So if you want to make a compact spherical grain, what can you do? Well, you can do theory. If you want to put mantle, well, you can use the method which is called BH coat, and you will find the recipe in Boren and Hoffman. If you want to make composite grains, you can do it using a random distribution of your material. Or if you want to control where your material are, you do something more complicated and longer with a discrete dipole approximation, etc. So you have many ways of doing that, and you choose it according to the shape you want to calculate, but also to the material you are choosing, because you will not treat similarly a conductor and an insulating material, etc. So this is another source of uncertainty. Which method do I choose? And we know that some of them are good at some wavelengths, or for some materials, or for some shapes. So you have to make a choice. So here it's an example. So I took Karine's silicates, the ones she showed before. So I'm a bit more brutal than what she is. So I say, okay, I have plus minus 10% of my optical constants. So what does it give? So here I calculated absorption and scattering efficiencies for 0.1 micron compact sphere. Using this plus 10 minus 10% uncertainty. So when you look it in log, you say, okay, that's fine, doesn't move much. But when you plot it, it's a ratio. So sorry, it's well, it's oh, what did I plot? I didn't write what I plotted. Sorry. sorry. Well, it's uncertainty on the resulting cubes probably. And you see that you find again your 10% at long wavelengths, but it's a bit more complicated at shorter wavelengths. Okay. And well, this does not speak to you probably. So if I do an SED with that, so I put a Matisse radiation field and I do an SED, I take a standard size distribution. So the SED is on the left. So in blue, you have my silicates, the ones that were before. That's SED. And if I add other populations, small carbons, big carbons, I get the black curve. And you see that, so if you look at that, at long wavelengths, if you look only at the silicates, you find again your 10% uncertainty. But if you start adding other populations, then it's lost. So it doesn't really matter. However, you see that it changed the peak position simply because since they don't emit the same quantity of photons at long wavelengths, they don't have the same temperature. So you will have a larger uncertainty around the peak of the SED, okay? But if you are only interested at what happened in the 3 millimeter, maybe it's not very important. It's important, but maybe. Now another example, the structure of the grain. So here what I did is, again, I take a silicate and it has a size equivalent, which gives you a mass. Well, so if I take a sphere of 4.1 micron, it has a given mass, and I do a lot of structures, and all have the same mass as this sphere. Okay, so I can do the compact sphere, so which is the black, and here what I plot is the mass absorption coefficient at 500 micron. So on the left you have the compact sphere, then you have the compact oblate, the compact prolate, a porous sphere. So the dispersion shows you if I put 10% porosity and up to 40% porosity. Then you have an aggregate of compact spheres, an aggregate of compact oblates, and an aggregate of compact prolates. So you see all these grains, they have the same mass, but their mass absorption coefficients, so their emissivity in the far infrared, can vary by factors of 2 to 3, okay? So this is another source of uncertainty. How do I, well, what do I decide? Do I have a sphere, simple, or do I have something more complicated? And of course, this will change the dust temperature a lot. Huh? So you will have, when you go from left to right, you will lose several Kelvin. So you will shift the peak of the SED by a lot. Then you can be a bit more picky and you want to say, okay, and what happens when I describe the grain surface differently? So you can describe it completely smooth, okay, or irregular. So here what I plotted is the extinction efficiency. So here in orange, you have a sphere of 4.1 micron. And what I did is that I describe their surface with a resolution of 2 to 14 nanometers, okay? And here you have the variations. So this is 2 and this is 14 nanometers resolution. So if I plot a ratio with between the irregular sphere to the perfectly smooth sphere, you see that you can have variations in the far infrared, which are of the order maximum of 5%. Okay, so that's another source of uncertainty. How do I describe my surface? And okay, to confuse you a bit more, here what I plotted also, here where I wrote 7%. So now if I take an aggregate, and well, this aggregate, okay, I say my aggregate, it has 6 0.1 micron monomers. There are many ways of arranging 6 monomers to make an aggregate, even if you keep the fractal dimension constant. And here, so you get, here I took 10 random arrangement, and so you have a dispersion in the extinction efficiency of 7%. And if you compare to the sphere of the same mass, you see that you have a factor of 1.5, more or less, okay? So that's another source of uncertainty. When someone shows you an aggregate model, you have to remember that this person chose an arrangement for his or her aggregates. And if you don't have this line plotted, you don't know how it varies. And the last example, well, the choice of the calculation method. So it's a bit more complicated, but anyway. So here what I plotted is, well, I want to make an aggregate of 8 monomers. Well, there are two sizes. Let's look at the smallest one. So the pink one, which has 0.1 micron monomers. And here what is shown, so you have 3 types of calculations. So you have discrete dipole approximation, which usually is considered as being more or less exact. So this is the straight line that you see. And you have a sphere with the same mass of your aggregate, compact sphere, which is plotted with crosses. And you have a clever way, a bit more clever way of doing that. So you assume that the radius of your sphere is the gyration radius of the aggregate, and you find a way to describe an equivalent porosity of the aggregate. So this is a bit more clever, and you can do that to have fast calculations. So here I plotted that for silicates, carbon without carbon poor in hydrogen and carbon rich in hydrogen. And so you have absorption efficiency, scattering efficiency, and here a ratio of the exact method, DDA, divided by the other method. So you have Q over Q. And what you see is that, so if you do a sphere, of course, it's really bad. You have something which is completely off. But also when you try to do something a bit more clever, you always have differences. So sometimes it's not bad at some wavelengths. So you see here we have the clever sphere is not so far away from the real aggregate in the far infrared. But when you go in the visible or in the UV, well, I don't even plot the UV here, sorry. So if you go in the visible, let's say, you don't have the same. So if you don't have the same visible extinction, it means that your grain cannot have the same temperature, of course. So again, you change your SED. And you can, well, it's not very easy to see, but you see that there is, here you see a lot of variations here around 10 micron. And it's known that the silicate bands, for instance, are not well reproduced by approximating methods. No method does that well. And I don't have any conclusions, so I just stop here.